Most people think the logical qubits to physical qubits ratio is sometime in the hundreds to thousands. We've shown 12 logical qubits with 56 physical qubits. Our overheads are that low because we start with very good quality qubits to begin with.
Many companies call 2025 the year of quantum computing, for reasons ranging from PQC to better applications in hardware. Here comes the Helios system from Quantinuum, and I say it's all right to celebrate 50 logical qubits this year. We look at the company's roadmap, aggressive error correction ratios, and some innovative ways the coming systems will work with AI to solve problems and not just generate hype. In this episode of the Post-Quantum World, I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our guest today is the CEO of Quantinuum, Rajeeb Hazra. Welcome to the show.
Thank you so much, Konstantinos. Great to be here and to be able to talk to you about this exciting world of quantum.
Yeah. Quantinuum's a major player, so it's always great to have a chat. I've been trying to set this up for a while, and it never seemed like the right time. There was like one announcement and another, and now we've got a new roadmap, and I think it's time. I think it's time for sure. We have a new year coming up, and I'd love to get your thoughts about a lot of things. So we'll dive right in. Let's start a little bit with what 2024 was pretty well known for, and what going forward will be known for. Logical qubits. We were, for a very long time, dreaming of these things. And then all of a sudden, they just started popping up everywhere. Boop, boop. Well, of course, there's a lot of work behind it. They don't just pop up. So maybe you could tell us a little bit about the logical qubit journey at Quantinuum, how it started and how it's going.
Yeah, that's 2024 has been exciting. And if it's any indication, 2025 will be even more exciting because of the pathways laid down in 2024. You asked a very interesting question, even though you couched it in the specific details of logical qubits. What it really comes down to is how much progress have we as an industry, and we particularly as Quantinuum, made in getting to universal fault-tolerant quantum computing. Because as we all know, if we can get there and produce things at scale, there are tremendous use cases and problems we can solve that we can only dream of today. But today's computers in the NISQ era, we spend a lot of time correcting for errors rather than solving the problem.
Yeah, definitely.
There are some players who believed that you really can't do anything useful till you get to fault tolerance, logical error rates of 10 to the power minus 8, 10 to the power minus 10. Until then, it's really just more R&D and science. And we actually see it slightly differently here at Quantinuum. We see the ability to start building algorithms and ecosystems happens even in the NISQ era before you get to full fault tolerance. And our goal is actually to pull that future in, which is exactly what we did, and announce a new roadmap. If you notice, this is for a company that has existed for 3 years in an industry where everybody announces roadmaps every 6 months. And for a company that's actually part of it has been in quantum computing, building hardware for over 10 years under Honeywell. Mm-hmm. The first ever public roadmap was a little strange, right? It's like, why haven't you guys talked about roadmaps before? And it is because we wanted to be dead sure of from where to when we were going to pull that horizon of universal fault-tolerant quantum computing in, and have confidence that we had the technologies and the technology paths identified and vetted to be able to state this is when we think, which is precisely in 2029, we will have hundreds of logical qubits over a range of logical error rates, some of them as high as, or error rates as low as 10 to the power minus 10. Right? Till we got to that, we weren't announcing a roadmap because we wanted to be very sure we would get there first. Mm-hmm. And it took multiple generations of systems to build them, to see how they work, to experiment with error correction and physical qubits. to get there. So our journey started really a long time ago. We knew we needed to get to universal fully fault-tolerant quantum computing. And we needed to get to a very specific set of physical qubit fidelities, more importantly, 2-qubit gate fidelities, before we said, hey, you can just do error detection and correction, and that's how you build logical qubits in some sense, that are better than the physical qubits. Otherwise, what's the point of building a logical qubit if its error rate is just the same as a physical qubit? And so we've labored, that journey started with building the world's highest physical qubit machines in themselves, our H1 machine, our H2 machine. And then as it crossed the thresholds of 3 nines, we actually demonstrated 3 nines first in the industry on H2, our 56 qubit current generation machine, and build it up to that level. And then said, now we can effectively run error detection and correction codes, quantum error correction, to get to even higher levels of fidelity on logical qubits with low overhead. Most people think, as you see the announcement we made with Microsoft, that most people till then, and still continue to write, that logical qubits to physical qubits, that ratio is sometime in the hundreds to thousands. We've shown 12 logical qubits with 56 physical qubits. Right? So
that is a really small ratio.
Our overheads, and they are that low because we start with very good quality qubits to begin with. Right? Mm-hmm. So our journey has always been a belief, number one, that you need very, very high quality qubits, not just a lot of trashy qubits. And then as you scale the number of qubits without taking the fidelity of those qubits down, you can bring in and mature quantum error correction very effectively. And so far, we've proven that. And that's what has helped us build the confidence to this machine we call Apollo, where we believe with thousands, not hundreds of thousands of physical qubits, we will get to hundreds of logical qubits. The second thing that we've said is, as we look at use cases, it isn't the case that you need one logical error rate. There are certain use cases and algorithms that are shallow, as we call them, the circuits, that would be fine with 10 to the power minus 5 or 10 to the power minus 6 error rates. There are some, and particularly deep chemistry kind of things and materials kind of things, that will need 10 to the power minus 10 or higher. And so we've designed Apollo to have that trade-off space where on the basis of thousands of very, very good physical qubits, you can design the machine to give you fewer logical qubits with very, very high fidelities or larger number of logical qubits with lower error rates. And so it's a way to attack a class of problems versus just build it for one problem and have the others who could have lived with relaxed constraints pay the tax for it.
And do you envision that like sort of Cubit Slider being something in the software stack that a user does directly? Or do you anticipate some kind of evolved system where you enter your circuit and the system says, oh, she doesn't even know what she wants here. Oh, he's not even sure what he wants here. They actually are looking for this many qubits, and it'll kind of like give you what you need.
Yeah, no, you asked a very good question, which is kind of gets us into this, what we talk about as how would these systems get actually coded? How would you present the algorithm? Is it a deterministic, I wrote the code or created the circuit? We already have tools in place called Toolkit that we've had over 1.8 million downloads now, where people write a raw circuit and then it gets optimized for, this is really the number of qubits you need. This is the all-to-all connectivity you need. This is the optimization of the circuit, and you run it. So we've already automated that piece through Toolkit. And then what we'll be adding as we add this tremendous hardware capability is the ability to have the system itself working with a classical partner, generate those circuits to optimize them, right? You generate a circuit, you get quantum data out of that circuit, and you say, no, I need to now modify it. So it starts to move towards self-coding systems, along with the hardware getting that capable.
Yeah, we do ultimately envision this being very abstracted out, like exactly. Libraries of circuits, sort of like we call we call libraries now encoding all the time, import,
Yeah, I
whatever.
mean,
Yeah.
if you look at, and that's how we are building full applications, or we see full applications being built. If you look at our in Quanto chemistry, some people call it an application because it pretty much has VQE and all of the phase estimation, the standard tools of quantum chemistry built into it. And so you can obviously construct. I think of us as building libraries like the numerical recipes, if you're used to that, or MATLAB as a toolbox, right? And then whether it's quantum DFT or some of the optimization QAOA kind of things, QML libraries, you build these libraries that people string together. And the way of stringing together 10 years ago, when I started coding 30 years ago, well, I won't tell you when I started coding, it'll give away my age. But you wrote a deterministic program. And now it's about, you have AI tools that says, out of these libraries of tools, what can we construct in a closed feedback system, and then get to the best and most optimal circuits, or the most optimal program.
Yeah, and in a theme with all this here, aligned to all this, the ticket, so it's spelled TKET for listeners. Just recently, as we're recording this, there was also released the quantum error correction decoder toolkit, and I'd love to hear a little bit about that, and then also just dive into after a little bit about how error correction has evolved. Because as you mentioned, it did start with this Microsoft experiment that got us that real high result. But it sounds like quantum error correction decoder toolkit does a little more than that. It gives you opportunities to bring in other types, right?
Yeah. So let me, you mentioned a number of related things. So let me parse those apart and answer each of those as a question. So we're very proud of the quantum error correction toolkit. As you said, it's a very recent thing, and we put it out, and it's really aimed at experts today who are looking at how to use the features of a very powerful piece of hardware, right, today, like the H2 machine, and start to build quantum error correction codes on them, right? High error rate or high rate codes versus low rate codes, expose the ability to use the features like all-to-all connectivity and mid-circuit measurement. So it's like an SDK that says, here's all the great features of the hardware. Now, if you're an expert, go build. Over time, we see people who aren't that deep experts at the edge of quantum error correction also use this toolkit to say, for my application, is there a more ready QEC algorithm ready, and let me bolt into it, right? Or let me bolt that into the application and then go execute on the hardware. So we think it is both a research accelerator for quantum error correction, but it's also a democratizer, because then as more quantum error correction capabilities present in the toolkit, it can be used for applications, which is now specifically tied to the hardware, which is through a compiler, as you well know. Someone's got to write the physical compiler. And most error correction folks, that's where it breaks down. If it is, you write it in an abstract sense without fully understanding the microarchitecture and features of the machine, and you don't make the best use. We succeed very well in quantum error correction because we are a full stack company, and we can change the hardware and the software. The hardware is changed through compilers that can get the best out of a high rate code and make the right optimizations across the different memory types, for instance. Is it crosstalk that I have to minimize? Is it state preparation that I have to minimize? Is it memory errors that I have to minimize? So that's why we see it as a powerful ecosystem tool that accelerates QEC, but also makes it available for democratization. The question you asked about our journey in QEC, didn't start with Microsoft. Right? It's a great partnership. They've had their own quantum error correction, and this is an amazing proof that you need really what the best of class hardware today can provide in order to write, to be able to get 12 logical qubits. But we have our own approaches to that as well. Because we've always believed that NISQ is not a useless phase, that everybody has to wait till you get to fully fault tolerant. And number two, you don't get to fully fault tolerant, you don't get to accelerate to that future if you're not working on error correction.
Yeah, absolutely. And so in some ways, this feels like it could be a crowdsourcing of best paths forward for error correction, like getting people
Well,
to
I
try
think
things and
I
seeing
would
how.
love to tell you, Konstantinos, that there's a crowd in anything in quantum. One of the challenges we have is scarcity, right?
Yeah,
But we
yeah.
do see it absolutely growing, right? As you know, today maybe you can count the number of people doing leading edge new quantum error correction codes, high rate codes on the tip of your hands,
Hmm.
right? But we see it increasing very rapidly as it matures and subcodes get created or a hierarchy of codes get created, like concatenated codes get created, right?
Hmm.
So the building blocks are there, and then people start to do interesting combinations of concatenated codes, and suddenly the industry's grown. I mean, it's got to grow from something. So why not energize that with this toolkit?
So right now, this lets end users potentially come up with results that you haven't seen yet.
We're already seeing that, not
Yeah.
potentially. I'll take the word potentially out, right? I mean,
Nice. Okay.
um, one of the things that Microsoft did show, and this is a very interesting um, kind of segue into an area that I think we absolutely have to talk about, is most people have thought up until now, till Microsoft and us announced this, that you really needed, if you were just using quantum computing, you really needed lots of qubits and lots and very low error rates, or very high, essentially fault on quantum computing to do, say, quantum chemistry for
Hmm.
anything useful. What that line of thought doesn't understand is there are more tools than just computing. The other tool is AI.
Hmm.
So what we showed was, in combination with classical machine learning and artificial generative AI, just take it as generative AI for a second. Uh, these very powerful LLMs, or LQMs, as Jack Hidari at Sandbox IQ would call it, are much more powerful if they are trained on data that isn't an approximation of chemical processes. If they can actually see the state changes that happen as a chemical reaction, as a as interaction of multi bodies happen at the quantum scale, they get to, to be far more capable in the inference and prediction of what is right and what is wrong. So I akin it to somewhat like, if I had cataracts and I couldn't see fine detail, I could only understand the world as blobs and maybe predict it in terms of blobs. My accuracy would be at that level. But what quantum computing does is suddenly adds the ability to take that cataract away and let me see phenomena and see the data from that phenomena of multi-body interaction, that the quantum scale that I could have never seen before, so I could have never trained on it before. So I go from gross approximations to much finer level of detail of training, and suddenly I can now enable a much finer level of inference. So, for instance, if I can see that accurately and generate the quantum data, maybe my initial set of molecules that I'm looking at, say, to create a new refrigerant, right,
Hmm.
doesn't have to be as large, because I've already cut the state space by understanding, based on the constraints of the problem and the molecule set, that I don't have to look through all spaces.
Okay. That
So
makes sense.
what quantum is doing is essentially making Gen AI have more powerful training. It's like Gen AI used to go to high school. Now it's gone to like college to get a set of training that it could never had before.
So it's a pre-processing of sorts that you're
Yeah.
doing.
And suddenly it's no longer, I have to, it's giving enough data for the AI agent to be far more effective and efficient, rather than just doing quantum chemistry from beginning to end.
Yeah. So when we had D-Wave on, they were talking about using optimizers to help the power efficiency of training. And then now you're talking about using the AI that's been trained to help cut down on what has to be fed to a quantum computer, basically,
Right.
which will also save power in the other end.
Well, it saves, it saves on total time to solution. And in some of these hundreds of billions of dollars of industries like pharmaceuticals, right, or specialty chemicals, we're not talking years, and it's a very simple argument, right? I get a patent. That's what I'm going to monetize. I have a 20-year life on a patent. So if it takes me 7 years to actually create the drug, go through trials, I only have 13 years of life left. If I can cut that down by half, that 7 years down to even 3 years, I have 3 years or 3.5 years in that case of extra value life. That's billions of dollars of additional value to me.
Yeah, that builds in all the time for regulatory bodies to completely stop the process.
It's really quantum accelerating an AI-driven discovery process. And that can apply in so many different industries. And that is what we think is the huge, huge promise of, or the blessing that we have of having Gen AI be as mature as it is right now, even though some people would say it's in its infancy, and they're right on a long-term scale. And number two is that we have quantum mature enough and producing at scales of both qubits as well as fidelity levels that you can do something really, really useful with it.
Yeah, and this is a very defined use case. Like, you don't need a mixture of experts. You don't need any kind of those approaches to LLMs here. You're just focusing on one type of
or a general class of problems, right?
Yeah, exactly. At a time.
And then of course there are places where absolutely quantum, think of it as an accelerator, as you just said, is more energy efficient, right? For instance, if you were to take the transformer pipeline in a standard, convolutional neural network, the transformer-based approach in an LLM, and take that transform and represent it as a tensor representation versus the classical neural representation, you can execute that same classical transformer on a quantum computer, spending kilowatts of energy, not megawatts. Right? So,
that brings me to something I wanted to discuss when we started the Gen AI topic. This year, there have been the first quantum transformers, let's say, right? Are you actively working on implementing transformers right now? In creating...
Yeah, we are actually absolutely actively engaged in not just the research. Some of the folks that created the original transformer technology, and then its quantum representation actually work at Quantinuum. Stephen Clark, particularly, who heads our AI work. So we're actively looking at that. We're actually looking at sizing what the gains are. So we look at that part of the work, and we actually announced some work that we can make sure you have it, where we looked at it was called Quixer. If you go look at talking about how we can do quantum transformers or quantum to make transformers more efficient on resources. So it's a very, very active area of research for us, because what it doesn't change classical AI. It just says there's a better way to compute on classical AI with a different representation versus having to come up with a completely new representation of insight and knowledge.
And my hope is for both performance increases, of course, but power savings.
Yeah. Some of the things that we are able to show today is our full quantum computer H2, which can no longer be classically simulated. So there's not the largest supercomputer in the world cannot simulate the state vector representation of our existing current generation quantum computer, right? Because it gives up at about 40 qubits. That's gets prohibitive to do that. And
for state vector, you as you approach 50, it becomes a nightmare. There are other things, other simulations with tensor.
Even that computer can now do things that you therefore cannot classically simulate and get the data out, and with megawatts of power, and we do it with kilowatts, like 20, 25 kilowatts of power. So look at the tremendous energy efficiency of that portion of the pipeline. The other one we looked at was we had a paper on certified randomness that we wrote, and we said we challenged a This is the one that was 100x better than what Google published in 2019.
Yeah, it was to get a 30,000 x reduction in
and
power
uncertain
consumption,
sampling
right?
is the benchmark, and that we showed that we were 30,000 times more energy efficient. It wasn't just 100x better in terms of where better is defined as more accurate as an output, but it was also 30,000 times more energy efficient.
Yeah, and that's a major point because there have been some articles written recently where they talk about why do we need quantum? We'll just be able to figure everything out with AI eventually. And I joked on X that, okay, just build a nuclear reactor on every block so we could power AI to try and simulate everything. It can't be done.
Exactly. I mean, and I think there's a real concern around two things around Gen AI as we see it. One is the sustainability perspective, as you were just talking about. Do we need a nuclear reactor next to every training data center, for instance? And the other is what I call responsible, right? Responsible in terms of, is it explainable? Is it transparent? I mean, these LLMs now make decisions which are hard to understand as to how, which is why you see in regulated industries, deep in the core of banking, for instance, they're still reticent to use. You're not going to ask an LLM, can you optimize my $1 billion portfolio? Because
absolutely.
You sure as hell want to know why it made
Yeah. And just regulatory, right? Sometimes you have to be able to say why you made a decision.
And today's representation of knowledge inside a convolutional neural network and the process of training, which is, it's supervised and then reinforced learning, right? Because as it actually works, it incorporates the feedback to actually train the model. It is fundamentally non-transparent. And there we are also working, and this is a little bit of long-term research, but is there a different representation? And we believe there is, of knowledge, which is not along the lines of a neural network, which actually gives you both the ability to predict, but also gives you the transparency, because you can see in the model how it made the decision or a series of decisions more clearly than, say, a feed forward and forward and backward propagation across billions of parameters.
So there are two kind of like far-thinking quick questions I have. One of them is, I just want everyone to understand that H2, those are 56 all-to-all connectivity qubits, right?
Yes.
Like they can all just... And how does that affect the roadmap going forward? Is the goal to, when we get to Apollo, have it be all-to-all connectivity?
So the one thing is, if you look at just... I'm a classical computing guy by training, so I tend to use analogy.
Intel and everything, yeah.
Yeah. But we have kept, even though we've changed the microarchitecture of our machines, that is, the trap design is different, what is architecturally visible has stayed consistent from H1 and will stay all the way to Apollo. And what do I mean by architecture? These are things that are visible to you, the compiler, writer, or the programmer. Right? And we haven't changed that, even though the computers have got 1 trillion times more capable because of the changes in the microarchitecture, how we've changed the trap, the optics, the control mechanisms. We've had the features are all-to-all, mid-cycle measurement, and conditional execution, essentially, conditional qubits, and qubit reuse. Right? That is, these are the things that people have come to rely on will exist in our machines. They will always exist all the way through Apollo. So H1 had all-to-all connectivity. H2 has all-to-all connectivity. Helios, which is the next one we're preparing to release in mid-25, will have it. So architecturally, it'll all look the same. There is a really long-term question out there, which is, sometime when we get to millions or tens of millions of qubits, and we will get there, right? Maybe 10 years or a decade out or a little bit more than that. Do you need to have all-to-all? Or at that point, you have essentially enough qubits to chunk up the machine and use it for multiple algorithms at the same time. This is kind of like, now you have enough cores that you can have multi-tenancy on the machine, right?
And will it be one machine at all?
That's
right?
right. Will be
Might
one
be
machine. We
interconnect.
firmly
Right?
believe that you will have multi-tenancy at some point. That
Mm-hmm.
is, you're running multiple algorithms on different parts of the qubit set, right?
Mm-hmm.
And so you may need regional all-to-all connectivity, but not global all-to-all connectivity. And the regional is because tenant one is one region, tenant two is in another region, tenant three is another region.
Okay. And 2025, as you mentioned with Helios, we're expecting about 50 logical qubits. So that's
Yeah. Well, and again,
months
because
away.
we've demonstrated that we can improve, not only we start from a very low overhead. I mean, you're getting 12 out of 56, but we have codes now that we are confident that actually improves on that efficiency.
So this could be the year that we start seeing some type of advantage then coming forward.
Yeah, we certainly are working on that. I'm not going to kind of blow that surprise here, but
Uh-huh.
we are seeing multiple use cases, and it's not just us sitting in the lab. We are working with external partners on seeing some additional momentum towards quantum advantage in certain use cases.
That's great. That's a really optimistic note. And finally, because we talked about AI a lot, for a while it was kind of like this vaporware thing. It's like AI plus quantum, and it meant nothing. And literally, some companies vanished when they tried too hard to force that connection. So, do you envision going forward as we approach this like end of the decade? Really powerful system with Apollo. Do you envision the programming interface to have it all integrated? Do you imagine coding with the help of AI and then also having AI helping on the back end, like, oh, you need that, like on the back end?
Yeah, I think our vision is, I'll just state it very, very clearly, Konstantinos.
Mm-hmm.
Our vision is the highest value will be generated when you use AI on classical plus quantum in an integrated manner. I don't mean physical integration per se. I just mean the workload is integrated or the workflow is integrated.
Mm-hmm.
AI will be in everything. AI will, exactly as you said, AI will be in how you code. AI will be in the classical computer looking at fault tolerance, right? There are people using AI to build chips today. And
Mm-hmm.
there will be AI used to maintain uptime on those systems and keep integrity up at these large scales. I did HPC for 20 years, and I would have loved to have AI agents running that could look at the next bottleneck in the fabric and start to change, route packets differently. So there will be AI in all parts of the stack. But what we will see very clearly, because we are seeing it today, we will see it explode, is quantum helping AI be more two things or three things, I would say. One is more capable, simply because it will give AI the ability to have data that you couldn't get otherwise. It'll be more efficient because certain parts of the pipeline will run on the quantum machine versus the more power hungry classical machine. And third, at some point, and maybe this happens the last of the three, is it become more explainable and transparent.
Excellent. Okay. So with that bullet list and with the wonderful roadmap that you can see online, I'll let you go. And I'm looking forward to having someone back on as soon as you have an advantage paper to brag about this year.
Absolutely. Thank you for the wonderful discussion. It is the time. I know quantum has gone through its hype and then, kind of like, oh, now we're all depressed because we don't see everything we said 2 years ago come true. This is the most credibly exciting time for quantum. And the next 2 to 3 years will be transformational. And I guarantee you will see Quantinuum in almost all of those transformations.
All right. So I guess as we will wait for Helios, because here comes the sun. Yeah, thanks.
Absolutely. Literally. I may take that from you for our marketing. So.
It's yours to have, although I don't own the song. Thank you.
All right. Thank you very much.
Now it's time for Coherence, the Quantum Executive Summary, where I take a moment to highlight some of the business impacts we discussed today in case things got too nerdy at times. Let's recap. Quantinuum brought us 12 logical qubits in 2024, using only 56 physical ones. The team is preparing to unleash something even more impressive this year: 50 logical qubits in its Helios system. As we've mentioned on the show before, that number is significant as a barrier, as it is impossible to simulate more than 50 qubits with a state vector simulator running on classical hardware. 2025 will bring us to the edge of uncharted computational territory. Raj emphasized how Quantinuum succeeded by focusing on high-quality qubits and developing logical qubits with low overhead. Their error correction toolkit, which allows experts to create and implement new error correction codes, democratizes access to this technology. A key takeaway is the coming synergy between quantum computing and AI. Raj explained how AI can help limit the problem space a quantum computer has to tackle. For example, AI can pre-process and select a smaller set of molecules for a quantum computer to simulate to create a new refrigerant. Quantinuum also seeks to use AI in all aspects of quantum computing, from coding assistance to system maintenance. As the roadmap continues to evolve, Quantinuum systems are expected to maintain all-to-all connectivity of qubits, and even have multi-tenancy at some point. This would allow different algorithms to run on various groups of qubits in one system simultaneously. I'm excited for Helios Cloud Access to arrive this year. That does it for this episode. Thanks to Rajeeb Hazra for joining to discuss Quantinuum. And thank you for listening. If you enjoyed the show, please subscribe to Protiviti's The Post-Quantum World, and maybe leave a review to help others find us. Be sure to follow me on all socials at Constant Hacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protiviti. You can also DM me questions or suggestions for what you'd like to hear on the show. For more information on our quantum services, check out Protiviti.com or follow Protiviti Tech on Twitter and LinkedIn. Until next time, be kind and stay quantum curious.